Okay, here is your lecture, the rest of Chapter 4 on electromagnetism. So you can see here, there's some objectives. Make sure that you can answer the objectives. Make sure you watch the videos that I've posted. There's some other websites I've posted that are really good to help you understand these concepts. So, talking about electromagnetism. So, electromagnetism is electricity and magnetism are actually different aspects of the same force called electromagnetism. So it's electricity and magnetism combined together called electromagnetism. It's a combination of electric and magnetic fields traveling through space. So electromagnetic radiation, an electric and magnetic disturbance traveling through space at the speed of light. So anytime we talk about the velocity or the speed, it's the speed of light that is traveling at. So it results from acceleration of a charge. EM radiation can travel through a medium or a vacuum, and it's wave or particle duality and excitation and ionization also. So electromagnetic spectrum, so it's a way of ordering or grouping the different electromagnetic radiations. So members of the electromagnetic spectrum, they have the same velocity, so they're all at the speed of light, which is 3 times 10 to the 8th ms. Vary only in their energy, wavelength, and frequency. So that's what makes them unique. The range of energy, frequency, and wavelength of the electromagnetic spectrum is continuous. So if we look here with radio waves, when we're talking about MRI, we're using radio waves here. Then there's microwaves, infrared, and then you can see visible light is a very small area. And we go to ultraviolet, you can see X-rays pick up about here and gamma rays within here. So it's a higher energy. And those are the only two that are able to ionize. So electromagnetic radiation is a form of energy that originates from the atom. It can exist apart from matter and can travel through a vacuum. Energy and frequency of electromagnetic radiation are related mathematically. The energy can be evaluated as E equals HF. So energy ranges is from 10 to the negative 12 to 10 to the 10th power electron volts. So the lowercase e with a capital V. This is electron volts. The particle theory. So high frequency, high energy EM radiation interacts like particles when contacting each other. So photon energy and frequency are directly related. If frequency is doubled, energy is doubled. Planck's constant. So German physicist Max Planck has E equals HV, so the H is 4.15 times 10 to the negative 15 electron volts per second. So Oersted experiment is a build upon Planck's. So the charge in motion will create a magnetic field. So no charge equals no magnetic field. So if you can see here, if we're looking at this diagram, you can see the compass is pointing in the direction of the magnetic field of the force of the earth. If you apply a current within that area, you can see the compass moves with the current. So here, if we're looking, the relationship of induced magnetic field to the direction of the current flow, a variation of Oersted's experiment maps out the magnetic field inducing by flow of current. So you can see here how the compasses are lined up. Here is your current flow, and you can see your field around the current flow, and you can see your compasses are turning with the circle. So as it comes down and around, you can see the compass is pointing, and then it's making the turn here, so it's pointing, and making the turn here, so it's pointing there. When we talk about the Fleming's right hand or the Fleming's hand rules, we have the hand-thumb rules along a conductor, the hand-thumb rules along a solenoid, the hand generator effect rules, and the hand motor principle rules. So the hand rules are based on current flow. So conventional current direction, and hand rules are based on electron flow. Actually, direction of electron movement will be exactly the opposite. So we're looking at the right-hand thumb rule. So the thumb indicates the direction of the current. So here is the thumb and it's going along the conductor here, or the wire. So wire, conductor, same difference. So coming along the wire here, you can see that the current is going this way, which is the thumb is pointing, and the fingers are coming around here, which is your field lines. So the direction of the fingers is your field lines, or your magnetic field. The right-hand thumb rule, so or the hand thumb rule, so the left-hand thumb rule, the thumb indicates the direction of the electron flows, so here, and the fingers indicate the direction of the magnetic field. So you can see the field here and the current here. So this finger is coming straight at us. And there's a lot of videos showing you how the right-hand, left-hand rule applies. So this is the right-hand rule applied to a solenoid. So the right-hand rule to determine the pole of the solenoid or the electromagnetic. So when the fingers point in the direction of the current, the thumb will point towards the north pole. So if you wrap your fingers around the current here, going around and around and around, your thumb will point towards the north pole. So solenoid and electromagnetic. So magnetic properties are only when the electronic current is flowing. So if there is a current, there is magnetic properties. If there is no current flowing, it stops, so there's no magnetic field. So the current can be adjusted up or down, so the strengths change accordingly. And the factors that affect the effectiveness of the solenoid and electromagnetics is the diameter of the coil, its length, and the current passing along the coil. So those are the factors that affect it. So it is the diameter of the coil, the length of the coil, and the current passing through the coil are your factors. So electromagnetic induction, so it's demonstrated by Faraday, requires components, so there's the magnetic field, the conductor, and a relative motion in order to induce current. Methods to induce a current, so move a conductor through a stationary magnetic field, move magnetic lines of force across a conductor, or vary the strength of a stationary magnet through the conductor. So two primary laws. There's Faraday's law, which is actually the first law of electromagnetics, and Lenz's law, which is the second law of electromagnetics. So 4 factors of Faraday's first law. So the strength of the magnetic field plays a factor, the speed of motion between the lines of force of a conductor, and the angle between the lines and flux of the conductor. So there's also the number of turns in a conductor. Those are the 4 factors. With Lenz's law, it's induced current flow creates opposing magnetic field. So induced current opposes any flux changes. So that's Lenz's law. And 2 types of induction. There's mutual induction and self-induction. So there's 2 coils in mutual induction. There's the primary and the secondary. So you can see here we have the primary and we have the secondary here. Varying current supplied to the primary coil induces a current within the second coil. So putting a current to the primary induces a current in the secondary. Self-induction always presents in coils supplied with alternating currents, so constantly changing current polarity, so changing magnetic fields affects nearby turns in the coil. So inductive reactance, so the ability of an alternating current to switch directions, causing the opposing potential difference to induce against the incoming supply of electrons, and it's measured in ohms. Okay, let's talk about generators. They convert mechanical energy to electrical energy. They're composed of a conductor and magnets. So the components of a generator is the armature, magnets, slip rings, and brushes. So you can see here we have the armature is this piece right here, and then we have our north and south pole, so a magnetic field. We have the slip ring, which is this unit right here, and brushes on the side. All right. So when we talk about generators, we're going to talk about Fleming's right-hand generator rule. So the thumb points in the direction of the conductor or armature. is moving, and the index finger points in the direction of the magnetic lines or force field, and then the middle finger will indicate the direction of the conventional current. So this current is coming right at us. Okay, so when we're looking here, we have, this is what we call a sine wave. So here, sine wave. So this is the positive portion, this is the negative portion of the sine wave. So if we're looking at A is parallel to the lines, so you can see right here, our armature is parallel to the lines, so the EMF is 0, so we're at 0 right here. B, you can see the armature is at a 45-degree angle, so the EMF is rising, so it's coming up. C, it's at 90 degrees, so we're at 90 degrees right here, which is max peak EMF. Then we're heading down to D, which is back to the 45, and it's going back to parallel. So you can see we're starting to lose our energy. And then E, it's back to parallel, so the EMF is 0 here, so 0. And then if it keeps going back around, so we're at a 215 degree. For F, you can see the wire is at 270 degrees. I'm sorry about that. It's actually at 215. G, it's at 270, so that's maximum. And then it heads back. So you can see as it's flipping around, we're going positive and negative coming around back to full spin at 360. So we're rising, rising, rising. Max is when it's parallel, either perpendicular, and then coming down and around. So one complete turn of the generator aperture represents one cycle. So if we start here, we come down and then back to 0, and then up and around back to 0. So this is one cycle. So this is one sine wave. All right. So when we're looking at this, we're looking at our wavelength, our energy, and our frequency. So we also talk about velocity. It's a given because it's all traveling at the speed of light, which is 3 × 10⁸ ms. So here you can see we have a higher frequency and a unit of time. So there's more cycles of the generator in the same amount of time as there is here. So this has 2 cycles, so 2 peaks here, and this has 4 peaks. So it's a higher frequency. So wavelength. It is a relationship between the wavelength and the frequency is inverse. Wavelength is generally expressed in meters. The actual measure is typically in exponential form, so 10 to the negative 11 meters. So the frequency is generally expressed in hertz. Frequencies that are very long or very small are expressed in the exponential form also. Okay, so wavelength and frequency. Electromagnetic radiation exhibits properties of wave or particles depending on its energy, in some cases its environment. So you can see the amplitude. So we have wavelength here, so from peak to peak. The frequency is how many times, how many cycles within a period of time, and the amplitude is how high, how much energy is there. So waves are disturbances in a medium, so such as ocean, sound, etc. And the wavelength is measured in angstrom. The frequency is cycles per second. So US and Canada generators are usually operating at 60 hertz. The rest of the world is at 50 hertz. So if you go to another country, you try to plug in your stuff, you're going to blow it up. So wave equation. So frequency and wavelength are inversely related. So the velocity equals the frequency times wavelength. Velocity of all EM radiation is c. So it's constant, which is 3 times 10 to the 8th power meters per second. So that is your equation there. So, electromagnetic radiation nature and characteristics. So the basic formula for calculating wavelength or frequency. This formula is simplified when applied to electromagnetic radiation. So solving for frequency and solving for wavelength. There's your 2 formulas. And here, this is out of Taboo Song. I thought it was pretty good. So if you're having difficulty figuring out how to solve for the equation, it's here for you. And this is just a good example showing you the frequency and wavelength. So a small object dropped into a small pond, a smooth pond, creates waves of short wavelength. A large object creates waves of much longer wavelengths. And you can see here, energy is reflected when waves crash into a bulkhead. It is absorbed by the beach. It is partially absorbed or attenuated by a line of pilings. Light is also reflected, absorbed, and attenuated depending on the composition of the surface on which it goes upon. So, Ohm's law. Peak voltage is not the same as average voltage throughout the entire sine wave. So the same is true for amperage and resistance. It's difficult to measure in pulsating alternating current due to fluctuations in the sine wave. So we solve using root mean square, so RMS values of the amperage and voltage. RMS values of the total voltage and amperage in the alternating current are equivalent to the effect that would be produced in direct current resistance by the same factors. Apparent total resistance of an alternating current is called impedance, which is represented by the symbol Z. So here's your equation. You have your I, which is your amperage, your V, which is your voltage, and Z is your impedance. All right, commutator ring. So it's a single ring that is divided in half, with each half connected to one end of the aperture wire. So it replaces the slip ring. The armature turns exactly at the same alternating current as a generator. The sine wave does not drop, it stays positive. So here, compared to our last one where it came down and around and then it dropped down below and then met it back at the 360 0, here you can see with this new commutator ring, we're here parallel, so we're at 0, and then we go to 90 degrees, which is peak, and then we go back down to 0 here at C, so we're at a 180, coming back up, we're at 270, and then 360. So a DC generator, the slip rings have exchanged for a commutator ring, with each half connecting to one end of the aperture wire. Although the aperture turns exactly as the AC generator, the commutator routes the current as shown on the graph. So you can see it stays positive. So a multi-coil split commutator DC generator, it's more than one coil or armature with a split commutator. So you can see here we've got two on here, so we've got the one right here and we've got another one right here. So this is going to give us just a ripple effect instead of having big dips back down to 0. This is going to keep our voltage up at a higher, so this is a pulsed voltage, which is good. All right, so motors. Motors convert electrical energy to mechanical energy. Similar components to a generator, the armature is supplied with current and it has the motor principle. So the motor principle is the result of the interaction of the magnetic field when electric current is sent along a conductor that is residing in a magnetic field. So you can see here, as we're spinning around, you can see our north to south here. So Fleming's left-hand rule, if the index finger points in the direction of the magnetic lines of the force field and the middle finger points in the direction of the conventional current, the thumb will indicate the direction in the conductor will move. So the right-hand rule for flow of electrons. So remember, the actual current flow and the electron flows are opposite. So if you're looking at the electron flow, you're going to use your right hand instead of your left. So this is for your motor. Motor configurations, there's DC and AC motors. So the DC motors have the commutator rings. The AC motor uses slip rings. There's two types. There's synchronous alternating current motors and alternating current induction motors. So the synchronous is conducting coils that turn at the same speed as the generator armature supplying the current, and then alternating current induction motor. So induction there is important. Rotor coils with the exterior magnetic field supplied by several pairs of electromagnets, thus producing a strong magnetic field, increasing the power of the motor and permitting it to turn at any desired speed. So here is a picture of your induction motor. So the rotor consists of bars of copper around an iron core. No conductor or slip rings required. Instead, a stator is used. What is a stator? It consists of pairs of stationary magnets or electromagnets arranged around the rotor. The stator must be supplied with current, with multiphase current. So the anode spins on this concept. So this same concept is what we use on the anode. So here, the stator electromagnets, and then you have the rotor, and you can see it spins around and around and around. So different meters that we use. There's the galvanometer. So it measures, uses direct current and is used to indicate current. The dyno-nanometer uses alternating current, so it measures current, and the ammeter connects in a series and it measures current. Sorry, that's a T on the end, current. And the voltmeter connects in parallel, so it measures voltage. You can see here the galvanometer and the ammeter and a current, and then you have your voltmeter here measuring your voltage. So amperage, voltage, amperage. Controlling electrical current. So we have transformers, autotransformers, capacitors. So these three devices are now miniaturized in chip technology, which is really cool. So transformers, application of mutual induction and Ohm's law. So there's two coils. The current is supplied to the primary coil. The secondary coil is in close proximity, and we induce a field within the second, a current within the second by induction. So step up or step down transformers. When the secondary has more or less loops than the primary, producing more voltage or less voltage. So here, if we have, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 loops, and if we have 15 on this side, then it would be a step up. If we have 6 on this side, it would be a step down transformer. And it's important that you know the difference between the two. We are changing the voltage by using a step up or step down transformer. So voltage and the number of turns are proportional. Voltage and amperage are inversely proportional. The number of turns in amperage must be inversely proportional. Okay, so the transformer law. Voltage induced in secondary coil directly related to the number of turns in the secondary coil. So if we're looking at this equation here, with V equals the potential difference in the voltage, N is the number of turns in the coil, and P is the primary, and S is the secondary coil. So transformer law applied to Ohm's law. So currently induced in the secondary coil is inversely related to the voltage and number of turns in the primary coil. So transformer inefficiencies. So transformers are 95% efficient. So a high amount of wires and highly induced voltage causes several problems that affect the efficiency. So I2R loss. So that talks about copper and how there's a natural resistance within a conductor and it gives off heat. So as part of the 5%. And there's the hysteresis loss, so it's a lagging loss when dipoles reorientate to the magnetic field and there's some lag and it gives off heat with that. There's also eddy current loss, so current opposing the cause that produced them. So this is based off of Lenzs Law. So autotransformers, so a variable transformer, there's two designs. There's primary and secondary coils connected in a series, and there's single coil on a central core. So primary side allows for selection of active turns in the coil. So you can see here, and we can select which ones. The autotransformer is used to vary the incoming line voltage to an appropriate level for high voltage step-up transformers. The high voltage step-up transformer is used to rise the incoming line voltage to the voltage range necessary for X-ray production. So the filament is a step-down transformer. It's used to decrease the incoming line voltage to 5 to 15 volts to 3 to 5 amperage used to heat the X-ray tube filament. So looking here, we have your autotransformer. You can see we can pick which one. And then we have your step-up transformer. So you can see the coiling here versus the number of coiling here. So that tells you that this is a step-up transformer. And then coming through here, we have coming off here, we have a bunch of wires here, so we're coming in from the switch, and we've got a lot of wrapping, so a lot of coils, and we're only going to a few coils. So this is called a step-down transformer. So this one, on the primary side here, you can see we have only a few and a bunch over here, so this is a step-up transformer, and on the filament side, you can see we have a step-down. There's less wires than there are on the primary side there. All right, so capacitors. So they accumulate and store electrical charge. There's a simple design that's two metal plates, and they are oppositely charged. So the repulsion of the plates allows for more electrons to be stored on each, and they're separated by a dielectric, so like an insulation. So the unit of capacity is the farad. And the equation is C equals Q over V. So C is the capacitance in farads, Q is the charge in either plate in coulombs, and V is the potential difference between the plates in volts. So capacitors, they must be charged to be operable. They use direct current voltage, will accept charge until it reaches the DC charge. When discharged, the capacitor has the ability to deliver and store charge in short and easily controlled intervals, and it's used to supply a more constant voltage, to the X-ray tube. So we use the capacitors when we're working with the portables. Rectification, it's a process of changing AC to DC. So rectifiers, there's solid-state diodes, and vacuum tube rectifiers, there's half-wave and full-wave rectification. Solid-state diodes, they use a P to N junction with semiconductors. So the N type, they have loosely bound electrons that move freely between the atoms' conduction bands. The P type has electron traps made up of positively charged holes that tend to attract and hold electrons instead of permitting them to move around freely within the atom. So a diode has electrons flow from the N to the P side of the P-N junction, and conventional electrical current moves from the P to the N side. So here's an example. Here's the P and the N, and here's your junction. And you can see if you apply a charge to it, the negative is going to be pulled towards the positive. So you can see all of them went to the one side, and you have a junction here, so these guys aren't crossing over. And then you can see if we flip the charge, they flip the other way, okay? So they migrate of P holes away from the junction. And you can see this is our symbol for a diode, okay? So you can see here, this is the symbol. Thyristor, or silicone controlled rectifier, so an SCR. It's a GE trade name for a thyristor. It's more complex semiconductor, so you can see here. And a valve or a vacuum tube, the anode here, so you have your cathode and your anode, and you can see where your anode is being bombarded here. And the reason why we need rectification, it protects the current that can damage the equipment. So a negative charge at the cathode and a positive charge at the anode, electrons will flow from cathode to anode. This means conventional electrical current will always be from anode to cathode. So you can see your cathode here coming across to your anode. Half-wave rectification, so only half of the incoming alternating current is being converted to pulsating direct current. Opposing half of the flow is simply ignored or not utilized, so it's wasted. Electrons cease moving and stop transferring energy. So you can see here we have a diode that's sending, see your symbol for a diode, sending them back. Self-rectification, we don't like this, we don't use it because it can overheat the anode. This condition would allow electrons moving to the cathode filament during the half of the alternating current cycle when the anode was negatively charged. This could break the filament and destroy the X-ray tube. So self-rectification is not good. So you can see here self-rectification. Full wave rectification is converting the opposite half of the incoming electron flow so that the electrons are always moving in the same direction. So it does not discard the negative half, it uses it. Uses 4 rectifiers in a bridge circuit called a full wave rectification circuit. And you can see the picture here. We have the 4 diodes, so it's coming in. So it goes 1, 2, 3, comes around, 4, 5. So you can see it's constantly moving. All right. That is your PowerPoint for the rest of Chapter 4. The PowerPoint follows along the book perfectly, so read the book while going through the PowerPoint. Make sure you understand all of the outcomes or objectives for the chapter, be able to answer the questions at the back of the chapter. Very important that you fully understand everything. If you have questions, feel free to fire me off an email. You can ask Jerry. We're both here to help you through this. There's a lot within this chapter. It's the foundation, though, on how we're able to create our electrons and have our beam going from our cathode to our anode. So it's important that you do understand each component. Go to the ASRT and look at the circuitry and be sure to understand how it all fits together and how it works.